Aren't substitutions fun? We can take things that we don't know what to do with and make them look like something we do. It's a common mathematical trick, and we're going to keep playing that game today. What we're going to look at now are equations where we have this form. Our differential equation is in the form of some function of x plus y with coefficients. And we're going to look right away with what we're going to substitute for. We're going to say, hey, let's take all of this and make it equal to z. So z equals ax plus by. And what we're going to do is look at a few of these and see what they mean. So, for example, I have some combination of xy to the square root minus 1. And so the square root here makes this nonlinear, and I don't have the ability to work through it. And so what I want to do is, I'm going to go, hey, you know what? Let z equal x plus y. So taking the differential of z with respect to x, I'm going to get 1 plus dy dx. Right, because dx of x is 1, and this becomes dy dx. And so what I can do is I can substitute this back into my original differential equation here. So I can say, hey, well, I'll solve this, right? We'll solve this a bit. We'll say dy dx equals dz dx minus 1. I'm going to plug all of this in for dy dx, so I get dz dx minus 1 equals z to the 1/2 minus 1. And that's dz dx equals z to the 1/2. And I get dz over z to the 1/2 equal to dx. And if I use my power rule here, this is z to the 1/2. So if I integrate this, let's just bring it upstairs, z to the negative 1/2, dz equals the integral of dx. And so I want to go up 1, so z to the 1/2, but I have to divide by 1/2, which is the same as multiplying by 2, equals x plus c. I'm going to divide everything by 2, so I get x plus c over 2. But remember, z was our substitution, so I get x plus y, and I'll write 1/2 in its old-fashioned way here. And if I square this, I get x plus y equals x plus c squared. I'll make it over 4, and I'll bring this over here. Y equals x plus c squared over 4 minus x. And so we solve the differential equation by looking for the form where we had x and y as functions of x plus y. Let's look at one more of these and how this can be really useful. Plus, this gives us a thing. One of the things that we're kind of doing here is we're looking for patterns. And so some of these patterns we kind of have to dance around. And this particular problem from the textbook I liked because it made me aware of patterns that I knew. And that's why I said when thumbing through Shams, sometimes just knowing patterns is a good thing. And once you get used to the patterns, you can use them. And so, well, this is nice. I have x plus y as a function over here. So I'm going to say, hey, we'll make z equal to x plus y. And that means y is equal to z minus x. And dy dx is equal to dz dx minus 1. So I'm going to come back into here and I'm going to get dz dx minus 1, when I substitute all of this in up here, is equal to z plus 2 squared. Alright, so I'm going to say dz dx equals z plus 2 squared plus 1. And a little rearranging, dz equals z plus 2 squared plus 1 equals to dx. And here, this is where I really want to pause, and I want to talk about form. My instinct on this was to expand that back out. Okay. My instinct was to expand that back out and see if I could solve the quadratic that would come out of that. But what I want to do is I want to look at Shalom's 17.6.1 as my formula. And this is one of those things where you can get lost in the math rabbit hole if you're not used to certain forms. And 17.6.1 is the integrals in the form. So Shalom's 17.6.1 are integrals of the form of x squared plus a squared dx. But noticing that that is our squared term. I always have problems with this. Probably that's why I recognize it really. Try to recognize it as soon as possible. Because when I have something squared, my instinct is to, z squared plus 4z plus 4 plus 1. That would be z squared plus 4z plus 5. And then I'd fight with that, trying to figure out what to solve it for. And the thing to look at is that these are squares, and these follow this classic form, which is tangent inverse, right, of z plus 2 equals x plus c, and that means z plus 2 is equal to the tangent of x plus c, but z was x plus y. Let me subtract my 2 first, so tangent of x plus c minus 2, and then an x plus y equals the tangent of x plus c minus 2, and so y is equal to the tangent of x plus c minus x minus 2. And we've got our solution. And so there's another substitution of form that we can look at, substituting in forms of where x plus y, when we have functions of x plus y. Just watch your forms. Don't overdo the work.